Hello folks, this is Tom from anti-proton.com, and today we're going to discuss Europium-152. Now I'm currently in a basement. I know it's not the most luxurious place to do gamma spectroscopy, but it's incredibly temperature stable and the background here is pretty low. Notice that my Geiger counter is showing 32 to 36 counts per minute. Very, very, very low activity. So, which is kind of odd even though this is a cement floor. This is the place where I've currently put my detector. Let's pull out the Europium-152 and get started with things. Alright, so this is a poker chip piece of Europium-152. This is approximately 37,000 decays per second, 37 kilobecquerels, plus or minus. And this guy has a 95% accuracy in its activity. Pretty nice. So let's drop it here. And you'll notice that the Ludlum goes all the way up to, it's in the times 100 mode, so it goes all the way up to the 20,000 count mark. You notice the Polymaster's picking it up, and it's gone from a background of 0.0, 4 or 5 microsieverts per hour to 0.17, so yeah, pretty high. Several hundred counts per minute from the Geiger counter. Now let's talk about Europium-152 for a second. Europium in general is a pretty unstable element. Europium-153 is the most common. And Europium-151 exists too, but Europium-153 is stable, Europium-151 is not. Keep in mind though, it has a really, really, really slow decay rate. Europium-151 is so slow that only recently they discovered it actually decays, so it's nearly stable. See, as we put this closer, it goes up. Let's turn this to the times 1000 mode for a second, see where it goes. Anyway, there are 63 protons in Europium-152, and there are various splattering of neutrons. Europium-152 has 89 neutrons, for example, whereas Europium-153 has 90 neutrons, and so on. Europium-152, like this guy right here, was produced as a result of either a fission product. In this case right here, this guy is actually probably produced by neutron capture. They take another isotope of europium, blast it with neutrons, it absorbs a neutron and becomes 152, meaning it was probably Europium-151 to start with. But anyhow, it can also be produced, and typically is produced in nuclear reactors as a fission product. Although it's not a very common fission product, but it is nonetheless an existing one. Meaning after a nuclear bomb or a nuclear reactor meltdown, you'd find a little bit of this, but it would be overshadowed by a lot of other stuff. Anyhow, let's go into its decay. Its decay mode, well, before I say decay modes, let me say its half-life, which is 13.537 years. So about 13 and a half years to decay this by half. Meaning that, what is 13 times 7? Well, it's a big number. It's at least 70-something. In about 100 years, this will be useless. For my purposes, it'll actually be useless in about 20-something years. Anyhow, 1 gram of this stuff, if we had a gram, now we don't have a gram here for obvious reasons, but if I had a gram of this, it would be decaying approximately 6 trillion times per second per gram. That's 6.43 terabecquerels. So this stuff's pretty hot if you had a large amount of it, which we don't. We have a perfectly legal NRC exempt quantity of it right here. But anyhow, last but not least, I'll talk about its decay modes, then I'll show you the gamma spectrometer, and we'll look at what actually comes out of it. This guy decays 73% of the time by electron capture. It captures a really, really low orbital electron, sucks it on in, and gives it enough energy to convert a proton to a neutron, and it changes from Europium-152 to Samarium-152, which is stable. 0.02% of the time it actually does this via beta positive emission. So the forces between the protons and the neutrons are such that that energy can be converted all of a sudden into an electron and an anti-electron. The anti-electron goes flying off into the world for us to detect. The electron itself is immediately absorbed by a proton, again working like basically similarly to electron capture, giving it the energy to switch to a neutron, and then now we have, again, Samarium-152. So there's 2 ways that it can go to Samarium-152, which it does about 73% of the time, plus or minus. 27% of the time, it actually decays ironically by beta minus. A neutron turns into a proton, which I find kind of interesting that this guy does both. In fact, all three technically. And it changes from Europium-152 into something called Gallidium-152. I hate saying Gallidium. It's hard for me to remember to say it. I'm usually pretty good with my nuclide, well, actually element in this case, my naming of the elements, but I always have trouble with Gallidium, and I don't know why. But anyhow, Gallidium-152 is a slow alpha emitter. In fact, how slow is it? Its half-life is 108 trillion years, if I did my math right. And if I didn't do my math right, you can let me know about it. But if that's true, then that means that it takes approximately 7,827 times the length of the universe so far, the age of the universe so far, which for that stuff to decay by half. That's the universe's age, by the way, is about 13.8 billion years. So anyhow, now that we've gone over all that interesting information, let's play quickly with our detectors for just maybe about 30 seconds to a minute, and then we'll throw this in the spectrometer and see what we get. All right, so what happens when we put the alpha, beta, gamma detector over it? Wow. 63,000. So about 62 to 63,000 counts per minute. It's leveling off. Maybe a little less. So somewhere around 60,000 counts per minute plus or minus. Not bad. A lot of that, in fact most of that, in fact nearly all of that is beta. That's not so much because beta is the most common product. It's also because of the fact that Geiger counters don't read gammas very well. They do read them, but they only read a couple percentage at the very most of what comes out of this thing. The efficiency for it's pretty low. You're picking up mostly betas. Geiger counters love betas. Alright. According to the dose estimate here from my Polymaster, which, by the way, does not reference itself to cesium-137 like the Geiger counter does. This thing actually absorbs the photon energy and tells us. Let's see what the dose rate is. We'll give it a few minutes to get accurate on its dose rate. While it's getting accurate, let's look at the Ludlam for a second here. And kind of adjust this down. I've been having a weird malfunction with my tripod here. So, in fact, let me put something underneath the Ludlam so you can see a little better. Currently, the Ludlam, if I take the 44-2, which is a 1-inch sodium iodide detector, move it away from all of this mess, my background drops down a little bit. Let's cut the sound off of this and cut the sound on this. We're at about 2,000 counts per minute. It's actually a little bit less than that, more like 1,000 counts if I didn't have any of this material exposed. When I put the detector, it goes immediately hard over. On the times 100 mode, where you have 0, 10,000, 20, 30, 40, and 50,000, I go hard over again. On the 1,000 mode, this is a Model 12, so I can go up to 1,000. Yay. Let's see where I go. At contact, 400,000 and 500,000, and we are out of here. This source is a little bit over 500,000 counts per minute at contact with this Ludlam Model 44-2 on a Model 12. Not bad. Let's hear what that sounds like again, by the way. Wow. Anyway, this has had a little bit of time to get itself straight, so let's see what we've come down to. It's dropped down pretty low now. So this thing thinks it's about 5.7 microsieverts per hour, 5.6, somewhere in there. That's probably about right. You should double that if you wanted to calculate the dose for the entire source itself. Okay, so let's move our Ludlam out of the way. Now we used two detectors for this. We used a low energy, it's called low energy gamma probe, but it's actually mostly X-rays. This is an RAP-47 from, I put the Civil Defense sticker on it, from SC International. I used this guy right here. And I also used, detach my camera for a second, this 1.5-inch sodium iodide detector. You notice that I have lead shielding set up. I'm currently living with my in-laws while my wife and I are trying to get ourselves a house. The house will have a full nuclear physics laboratory in it, so until that time, I'm kind of in the basement here with a small amount of shielding. The rest of my lead box, my entire lead castle, is currently packed away. But until then, you can see we have a spectrometer set up here. This is a Spectrum Techniques UCS 30. So, nice little guy. And if we take the Europium-152 sample and hold it down here in front of the detector, watch what happens on the screen. Look at that. Look at those peaks rise, and they're very distinct. Well, I've droned on long enough. Let's get to the spectrum. Okay, so here we are in the spectrometer, and we're looking at an energy of 7 to 10, somewhere in there, kilo-electron volts, that's thousands of electron volts, all the way up to an energy of 2043 kilo-electron volts. So basically put, this is a pretty wide energy, and of course the detector I used for this was my SPA38 detector from Radiation Sensors. I got it from Spectrum Techniques. It's a 1.5 inch sodium iodide detector. 1.5 inch is pretty good for picking up these nice wide ranges. A little bigger would have been a little better, but you know, those are kind of expensive. Now we're looking at this in the logarithmic view. So 0 to 16 counts, and then 16 to 256, 256 to 4,000, 4,000 to 64, 64,000 to 1 million, 1 million to 16 million. You get the idea. This is a logarithmic view. It lets you see all the peaks. We could switch to a linear view, where this is exactly proportional all the way up. Let's kind of scroll down so we don't overlap. Smooth it out a little bit. And then as you can see in a linear view, it's some of these peaks like this guy right here and this guy right here are so pronounced that they kind of wash everything else out. You have to scroll all the way up here to make these other peaks appear, and when you do, these guys just overlap and overlap and overlap. So quite frankly, it's easier to just look in a logarithmic view when you have a particular nuclide like Europium-152. Now this is of course a spectrum of the decay energies that come from the daughters of Europium-152, not actually Europium-152 itself. Europium-152, whenever you're looking at any nuclide, you're looking at the daughters. You're not looking at the nuclide itself. So if we looked at a cesium-137 spectrum, what we're actually looking at is the decay energies, the excitation energies, if you like, meaning the excited state of the atom as it calms down. They would be what comes from barium-137M and barium-137. In this case, Europium-152, as I said before, decays into samarium-152 and gadolinium-152. I hate saying gadolinium; it's a pain to say. And so these gamma rays that you're seeing come from those daughter nuclei, if you like. So we can look at the energies here, but it's easier to look at the solved graph, which I'll show you in just a second. Just to let you know, some of these areas here are hard to actually see the gamma rays that appeared. What I did was I switched to linear view and I expanded them. And when they're very, very, very expanded and a little math is used, you can extrapolate a peak here and a peak here. And once you then switch back to linear view, these non-peak areas here actually end up having peaks in them that you couldn't otherwise see. So let's look at the solved chart now. This is the solved one. Notice, by the way, both of these two areas had peaks in them that you didn't see, but they're actually there. This is the entire spectrum completely solved. And I'll post a link to this if you want to download it and look at it. I think this might be useful to some people when they're actually doing gamma spectroscopy of a Europium-152 source. So let's kind of zoom in for a second and see where these guys come from. This stuff down here is mostly X-rays. You notice that everything from here all the way down is an X-ray. We have X-rays from samarium-152 all the way down here. These two guys right here are X-rays, and you notice when it says Ka2 and Ka1, that means that the K shell, if you like, of electrons, the K shell, the alpha 2 and alpha 1 electrons are the ones that caused these X-rays at these energies when they state changed. They do this after the I forgot to put a line in here. Well, look at that. Well, anyway, they both appear in exactly the same location. That's probably why I only put one line in. Basically put, these X-rays occur when after the Europium-152 is decayed into samarium-152. The X-rays themselves are the result of electrons filling in holes where other electrons have either disappeared or where the general waveform of the atom has changed. And of course, some of these guys occur via electron capture. And electron capture requires electrons to disappear from really, really low shells like the K shells. So these are atoms that are these are electrons that are moving into those shells. Atoms. Sometimes I just say the randomest things when I'm talking. So anyhow, the rest of these guys here are mostly from the actual decay itself. They're the result of it. The only other two that are weird are these guys too. These are lead X-rays. They come from the actual shielding around the detector. Now enough about X-rays. I'll show you some more of those in a few seconds, but let's get into the decay stuff. Gamma rays are not a form of decay. They're not emitted as an actual decay itself. They're the result of a decay. The atom's left in an excited state, and it has to calm down and relax. And to do that, it has to let go of that surplus energy. So when I say that this 148.01 keV gamma came from Europium 150, from EU 152 with EC, comma E plus. What I'm saying is that Europium 152 is the source. It's actually technically not the source. It probably came from, I can't recall off the top of my head if this came from samarium or if this came from gadolinium, I hate this one. GD152. I can't pronounce that thing to save my life. I hate that. There's several elements that I don't like to say, and that's one of them. Anyway, this could have come from either one, and I have to go look up in my book to see which one it came from. But it's the result of electron capture. Actually, that tells you right there. Electron capture means this came from samarium 152. And it also results from electron capture and beta positive emission. So that's where that guy came from. And this guy right here is a beta negative, and we know that beta negative means it came from GD152. So once Europium 152 decayed into GD152, this guy was emitted as a result of that afterwards in order to reduce the nucleide's energy down to a ground state. So here they are. Look how many gamma rays exist in Europium 152. Good grief. Some people have been led, including myself, to believe that Europium 152 is a good calibration source because it produces so many points, and this is true. But here's the problem. It produces so many different peaks that it can actually be hard to fine-tune your system initially to figure out, like, you know, if this is what you're looking at, or if you're actually looking at this group of 4 of them right here, because they can look the same if your calibration's wrong. So it's important to calibrate with something like cesium-137, which is what I did. I used cesium-137, which gave me a peak right here and a peak right here. And then I also used cobalt-60, which gave me 2 peaks here and here. And then I had some potassium-40, which is a peak right here. I used those to get this chart approximately right. Then I ran a short run of Europium 152 and then calibrated off of that. And then I ran the full 1-hour run. It's actually not as useful as you think, but once you have it calibrated correctly, you can then use it for more narrow calibrations of specific areas. So this is one of the nucleides I would suggest buying if you're going to be into gamma spectroscopy. Although I still say that cobalt-60 and your cesium-137 are more important. At the very end of the spectrum over here, we have some what's called random summing or pileup. This is just various high energy photons from further to the left that we don't see, who have Compton peaks and stuff that are piling up here and summing. It's also the summing of others over here, like the sum of this peak and the sum of this peak might equal this peak, and the sum of this one and this one might equal that, and the sum of this one and this one might equal here, and little bits like that, and other stray gamma rays, and they produce all this kind of pile of crud right here. So that's why it's called pileup. You'll see it a lot in spectrums. All right, so let's move over into the next spectrum I took, and this is the low energy. I used my low energy probe for this one. Let me zoom in. Zoom, 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 zoom. Okay. This is a low energy spectrum. We're in linear mode this time. Now let me show you logarithm it looks like. Here's logarithmic view. Here's linear. Linear view I think looks better, but the problem is we can't see linear view with the high energy probe because the variance between the peaks is just too great. But for the low energy one, it seems like it works out okay. And you see the highest peak we had here for a period of about a half of an hour came out to maybe around 17,000 counts. Not too much. This was with my RAP47 low energy cesium iodide thallium dope probe. And this is a low energy probe from SE International. I used it on my UCS30 again though. And you see we're looking at gamma or X-ray energies down to 6 or 7 keV right here and all the way up to about 291 right here. And these energies, we could see them right here. This is, if you were to take, let's see, if you were to take this area right here and make a square of it, that's what you see right here. All right, that's what you see. Some of the peaks actually blended together a little bit. So let's look at the solved version of this. Oops. This is the solved version of this. So this is this. Oh, let me lower it down just a little bit. There you go. See? Ta-da! And if you're curious how I came up with these two guys here, if you zoom in enough, you eventually see those peaks forming. So let's go over here and look and see what we have. Okay, from my lead shielding, I actually have two peaks around 10 and 12 keV. This is from X-ray fluorescence of the lead, meaning that high energy gamma rays from the Europium 152's daughters actually hit the lead and caused fluorescence, kind of like when you shine a black light against something that's kind of, light colored, it reflects back at you in the dark. Same kind of idea, except with really, 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 really high energy photons. Down here you can almost see a nub of something forming, and this is right on the boundary of what my detector can detect. There should be some 5 and 6 keV photons, X-rays anyway, coming out of the gadolinium. I can never say that. Gadolinium. I hate that nuclide. And samarium. And they would be down here, but we can't see them. They're too close to the edge of my detection. And some of the electronic interference from the wires and stuff can actually start making peaks down this low, so we don't worry about those. These guys right here, samarium 152 creates this X-ray. And again, this X-ray, we saw those beforehand, if you like, right here. Remember? So let's switch back. Again, this is more XRF from the lead. And again, it's the classic 75 to 85 keV from the lead. This actually is that peak that you see in almost every spectrum you'll ever see, ever. That big 75 to 80 keV peak. It's right here, always from the lead. This guy right here is the first gamma ray, and so on. Here they are moving off and like that. So quite interesting to look down into the X-rays of it. The problem is the activity is a little high, so I wasn't able to pull anything else out of here, but not bad overall. Anyhow. So that, my friends, this is, by the way, a logarithmic view of the same thing. That, my friends, is Europium 152. A very, very amazingly neat source to have in your collection of gamma ray sources for your spectrometer. It's not very likely to find this out in the real world, although if we were to take a trip to Fukushima, for example, we might be able to find some sitting out on the ground. A place like that, or it may actually exist. In a place like Chernobyl, it wouldn't probably anymore. Well, it would, but not in an amount that you'd be able to detect. It's too small at that point. So, yay. Very, very interesting element. This has been Tom from anti-proton.com, and bye-bye.